Hello and welcome. Today, we're diving into one of the most practical, high-impact questions in healthcare. What is the role of AI in personalized medicine, and how do you make it work in the real world? After a year of digging through pilots, randomized controlled trials, and FDA clearances, one approach stood out in both outcomes and ROI. Start with medication personalization, then scale through privacy-first learning. If you remember nothing else, remember that sequence. It's the difference between a cool demo and measurable impact in 90 days. Here's the counterintuitive truth. The fastest wins don't come from fancy imaging or broad diagnostics. They come from pharmacogenomics at the moment of prescribing. Almost all of us carry genetic variants that change how we metabolize or respond to common drugs. But most systems still prescribe as if we're all the same. Meanwhile, the Clinical Pharmacogenomics Implementation Consortium, CPIC, has already laid out evidence-based guidelines for more than 24 genes and hundreds of medications. This isn't experimental fringe. These are actionable, clinic-ready recommendations you can put in front of clinicians today. The stakes are enormous. Adverse drug reactions kill roughly 100,000 people a year in the United States. And for many drugs, genetics explain more of the variability in response than age, weight, or medical history. That's not a rounding error. That's a signal so loud it's almost irresponsible to ignore. This is where AI shines. Think of AI as the never-sleeping co-pilot at the point of prescribing. It chews through genotype data, the current medication list, comorbidities, even the patient's insurance formulary, and turns all of that into precise, prioritized guidance in milliseconds. Let's say a clinician is about to prescribe clopidogrel, and the patient has a CYP2C19 loss-of-function variant. Instead of just flagging a vague warning, the system quantifies the risk, recommends an alternative, suggests a dose, and checks coverage. It's not a pop-up. It's a decision partner. If you want concrete use cases, start here. CYP2C19 guided antiplatelet therapy, SLC01B1 guided statins, and DPYD guided fluoropyrimidines in oncology. The GIFT randomized trial found that genotype-guided warfarin dosing reduced adverse events by 27% in older adults after surgery. And the economics are real. Kaiser Permanente reported a return of over $4 for every dollar invested in pharmacogenomics, driven by fewer hospitalizations and emergency visits. That's not hypothetical ROI. That's running in the black. What makes this strategy so powerful is the compounding effect. You usually run the genetic test once. Then AI keeps reusing that information every time a new prescription is written. Each new medication is another opportunity to avoid harm, optimize dose, and improve adherence. Over time, those wins stack, clinically and financially. If you're wondering how to get started without boiling the ocean, use the 3-2-1 rule. First, start small, prove big. Pick 2 or 3 high-impact gene-drug pairs that already have CPIC level A or B evidence. In most health systems, that means statins, clopidogrel, and warfarin. Second, make it seamless. Deliver guidance inside the EHR using standards like FIR genomics and layer on AI triage so the highest risks float to the top without spamming clinicians. Third, measure what matters. Track reduced ED visits, fewer dose changes, better adherence, and time to therapeutic range where relevant. Build simple dashboards that update automatically, because your early data will be your political capital for expansion. If you want a 30-day proof point, pilot a single alert for one high-volume gene-drug pair in your busiest clinic. In a month, you'll have counts of alerts fired, clinician responses, early outcome signals, and you'll know exactly where the workflow friction is. That's how you de-risk scale. Now, once you've got that foundation, here's how you scale responsibly and fast. Use federated learning. Skip the giant centralized data lake. Train models where the data lives. Federated learning lets multiple hospitals collaborate on model training without sharing raw patient data. It's privacy-preserving by design, which means approvals move faster, partnerships become easier, and the legal risk plummets. And it's not just about privacy. It's about performance. Models trained across diverse sites generalize better than models trained on a single dataset, even a large one. Healthcare is local. Practice patterns differ. Demographics vary. A sepsis model that works beautifully in an urban academic ICU can stumble in a community hospital if it's never seen those patients. Federated learning brings that diversity into the training loop without moving the data. Look at the exam consortium during COVID. 20 hospitals across 5 continents trained a federated model for chest X-ray analysis. The result? A 16% bump in external validation versus single-site models, and a speed of deployment that traditional collaborations can't touch. They went from concept to a live model in under 6 months. In the world of multi-site health data, that's warp speed. There's also a massive risk reduction story. Healthcare has the highest data breach costs of any industry, north of $10 million per incident on average. When data stays put and only model updates move, you remove the biggest single source of exposure while unlocking collaborative learning that used to take years of wrangling. Where does federated learning fit best? Think risk prediction, radiology triage, and multi-omics modeling, where generalization is everything. Sepsis is a perfect example. If you train only on ICU data, you'll miss the subtle prodrome that shows up in the emergency department or on a med-surg floor. A federated model that learns across ED presentations, ward deteriorations, and ICU progressions captures the full trajectory. Technically, this is more doable than ever. Frameworks like NVIDIA Flare and TensorFlow Federated have matured. The real work isn't writing code, it's aligning people. You need agreement on data standards, model goals, evaluation metrics, and governance. You need to define who vets updates, how you handle drift, and what happens when a site's data is out of distribution. It's more diplomacy than engineering, but it's doable with a clear playbook. If you want a pragmatic starting point, keep it simple. Pick one prediction task with clear clinical utility. Say 48-hour readmission risk for heart failure. Recruit 3 to 5 diverse sites. Agree on a minimal common data model and a single shared model architecture. Run a short simulation on synthetic data to test the pipes. Then move to a 2-month pilot with weekly rounds of training. Pre-register your evaluation metrics and include an external holdout set to keep yourselves honest. And put audit logs in place from day one so you can trace what changed when. Tie this back to medication personalization and you have a 1-2 punch. First, you improve safety and outcomes at the point of prescribing using pharmacogenomics and AI. That's your immediate defensible ROI. Second, you scale smarter by learning from diverse patient populations without moving any raw PHI. That's your engine for continuous improvement. A lot of teams ask, why not start with imaging or a broad diagnostic platform instead? The answer is opportunity cost. Pharmacogenomics gives you real-time, point-of-decision wins that clinicians feel immediately, and it pays for itself. Imaging AI can be fantastic, but it often requires more infrastructure, more change management, and longer horizons to show financial impact. Start where the wins are closest to the prescribing hand, then expand. So if you're planning your next 90 days, here's a straightforward path. Week 1, pick your 2 to 3 gene-drug pairs and map them to your prescribing volume. Week 2, define your EHR integration and the AI triage logic. High signal, low annoyance. Week 3, stand up your dashboard with the outcome metrics you'll track. Weeks 4 through 8, run the pilot in a high-volume clinic and meet weekly with clinicians to tune the experience. In parallel, Line up 2 or 3 partner sites for a federated proof of concept on a single prediction task. Agree on the data schema and metrics, set up the infrastructure, and schedule a short training cycle. By day 90, you should have real patient outcomes from pharmacogenomics in your home institution and a federated model showing improved generalization across partners. That's the role of AI in personalized medicine when you strip away the hype. It personalizes treatment where it matters most, medications, using evidence that's already strong. It makes those decisions smarter, faster, and more consistent than any human can do alone. And it scales that intelligence safely through privacy-first collaboration. So the model you use next quarter is better than the one you use today. If you've been waiting for the right place to start, this is it. Launch one gene drug alert next week. Prove it in 30 days. Build the dashboard. Then invite a few friends to train together without sharing a single row of raw data. That's how you go from a great idea to a measurable, defensible program that actually changes care.